Welcome to the homework solutions video for topic 3.05. This is homework assignment 2, questions 7, 8, and 9 from section 6.4 of the textbook. So number 7, computer chips use binary codes to operate. They're made up of binary numbers, combinations of zeros and ones. We've got tables that show how many digits a number can have and the number of possible codes and what those codes are in binary representation. Because should all be used to binary, we have a clock that runs that way in the classroom. So we want to find the equation of the exponential function that models the growth of this function. So let's come back and we'll take a look at the number of digits and the number of possible codes. So this is not one where we have to enter all the possible codes. Even though they are numbers, that's simply a list. What we are looking for is the scatter plot so we can identify the exponential function that does this. So again, we make our exponential trend line with our equation. And as we saw in class, Google Sheets will only do its fitting with the base e. Your calculators can use any base whatsoever. So your calculator probably pulled up base 2, while the spreadsheet says e exponent 0.693, which is equal to 2. So this equation is fitted with this data is fitted with the equation e to the 2x. 2 exponent x. In that case, the domain, even though the function itself has a domain that's all the real numbers, here we're looking at the number of digits in a binary number. You're not going to have 0, you're not going to have negatives. So this domain is not all real numbers like it is for a general function. This domain is the natural numbers. 1, 2, 3, 4, and other numbers you can get by adding 1 to another natural number. And then the range is also a discrete range, not continuous, so it's not all the real numbers. You could say it's also a subset of the natural numbers. You could say the range are the natural numbers, but it won't use them all. It'll only use the powers of 2. 2, 4, 8, 16, 32, 64, 128, and so on and so forth. So how many digits are needed to have a code for each of the 104 keys on a standard QWERTY keyboard? So with these codes, you don't have to worry about the capital and lowercase because your computer can tell whether the shift key is held down, control key is held down. So we'll just stick with the 104 rather than going for the full ASCII pages. So how many digits do we need before we get to 104? We can determine that. We go back to our fit. We need to get up to y equals 104. So let's manually set our vertical axis to go up to 128, for example. And we'll manually set our horizontal axis to go from the minimum we're starting at. We can go to 5, and that's not enough. We can go to 6, 7, and there we go. At 7 digits, we get up to 128. That is the point where we pass 104. 2 exponent 7 is the lowest natural number exponent of 2. That is 104 or greater. So that finishes problem 7. We are now going to move on to problem 8. So problem 8 says, air pressure around a plane decreases as the plane's altitude increases. The data at the right shows the pressure in millibars that is exerted by the atmosphere on an object at different altitudes in kilometers. We need to create a scatter plot, find the exponential function and graph it on the same plot, then estimate the pressure at 15 kilometers, and estimate the altitude where the pressure reaches 500 and, as a separate unit, 50 millibars. So the 500 is interpolating, because that number is between the data sets. It's going to be somewhere between 5 and 6. And the 50 is going to be extrapolating, because that's beyond the end of this chart. So let's see how that plays out. We are going to insert a chart. And believe it or not, this will be an exponential series, even though it is decreasing. It's just going to be an exponential with a negative exponent. So here it's e to the negative 0.134. So that finishes parts A and B. How about plotting it with the graph? Part C, estimate the pressure at 15 kilometers to the nearest tenth of a millibar. So for this and the rest, it's going to be easier to switch to Desmos and our graphing tool. So we need to make note that our equation is 1043 and e to the negative 0.134x. So that's 1043 times e to the negative 0.134x. Let me make sure I transcribed that correctly. I said 3,4 out loud, but typed 4,3. Possibly because of that coefficient here. But now we have it. And we need to adjust our y-axis so everything fits. The highest value we have in our data is about 1,000. So we'll leave the lower limit alone, but we'll change our upper limit to 1,000. So estimate the pressure at 15 kilometers in altitude. That's going to be about 139.75 millibars. To the nearest tenth, 139.8. And then we are looking to find the pressure when it reaches 500 and when it reaches 50. So there's our y equals 500 point. That's at about 5.5 kilometers. And it reaches 50 millibars past the end of this graph. So we're going to have to keep scrolling, which Desmos makes easy. So that's at about 22.7 kilometers above the Earth's surface. So that concludes assignment 8. Now for 9. A biologist has been studying the effects of environmental stressors on a population of frogs. The observations are shown in the table. By what percent is the frog population declining every year? We want to determine the equation of exponential regression function that models the decline. And we want to determine the half-life of the frog population. And we said that's about 3 years. Estimate by interpolation. And then verify it algebraically. So let's take a look at how these appear when we graph them. So we will start with question 9. In question 9 here, we start by setting up our exponential function. So we'll get our exponential and we will label the equation. There we go. So it's 575, and then e is, or exponent, e to the exponent negative 0.224. So what is e to the negative 0.224? That number is about 0.799 or about 0.8. So this tells us that after each year that goes by, we are at a proportion of about 0.8 of the population we had the previous year, or about 80% of the previous population. So we're losing 20% of the population each year. So we had to do part B before part A with these tools, but that's what we're seeing. It is roughly a 20% loss of the population each year. And the half-life of the frog population is determined, or they say is about 3 years, which means if we take this factor and raise it exponent 3, we do get 51%, or about half of the original data. And yeah, we have used the, we can use that regression equation to verify it algebraically. We can also take that 575 and just divide it by 2. And we will see it comes in very close to 3. 575 over 2 comes in at 287.5. And if we have 575 times the exponent of negative 0.224 times 3, it is fairly close to that mark. There's a 6 frog difference, roughly. Much of that is probably because internally things are rounded. Internally the number is not rounded at 3 decimal places. So those of you solving this with your calculators would have many more decimal places to represent with your solutions. But this concludes the solutions to homework assignment 3.05, number 2.